The period of a pendulum is indirectly related to both mass and amplitude, but is directly related to the length of the pendulum. Here I have a 480-gram water bottle swaying on a 1 meter long pendulum. It takes 9.5 seconds for the water bottle to make 5 full oscillations, making the period of this pendulum 1.91 seconds. I have now removed 1/3 of the water from the bottle, making it now weigh 320 grams. As you can see, the pendulum has the exact same period of 1.91 seconds. This is due to the fact that force and mass are proportional, meaning that when mass increases or decreases, so does the force. I now only have 1/3 of the water remaining in the bottle, making the mass equal to 160 grams. Again, the pendulum has the same period as before. It takes 9.5 seconds for the bottle to make 5 full oscillations, making the period 1.91 seconds. I will now move on to amplitude. This process shows that as long as the angle stays 10 degrees or under, it will not affect the sway of the pendulum. Here I set my angle to 10 degrees, and as you can see, the period has no change. The period is still 1.91 seconds. I now have my pendulum's amplitude set to 8 degrees. You can see no change in the period once again. This is because if the angle of the pendulum changes, so does the distance covered over time. Therefore, amplitude has no effect on a pendulum's motion. The pendulum is now at 6 degrees. As you can see, still no change to the pendulum's period. Finally, we will move on to the length of the pendulum. I have shortened this pendulum to 0.61 meters, and as you can see, the period has also decreased. The period is now at 1.6 seconds, a third of a second decrease from the 1 meter long pendulum. The pendulum is now set at a height of 0.5 meters. This has changed the period of the pendulum to 1.48 seconds. This is due to the fact that the shorter the pendulum, the higher the frequency. This means that it oscillates more times in a given amount of time. For the last test, I've set my pendulum to 0.3 meters. This has changed the period to 1.2 seconds. With a certain applied force, you can see that I can only stretch them 5 inches. After adding just 2 more rubber bands, you can see that as I stretch the rubber band with the same amount of force, it stretches 7 inches rather than 5. I added 2 more rubber bands, and as you can see, if I stretch the rubber band with the same amount of force, it will stretch 10 inches. This all happens because as I add more rubber bands, the spring constant weakens, allowing it to stretch further. For this clip, I have attached a 240-gram water bottle to a 0.71 meter long band. As shown, the water bottle did 5 full oscillations in 6.65 seconds, making the period equal to 1.33 seconds. The bottle is now 2/3 of the way full, making the mass equal to 320 grams. This has increased the period to 1.48 seconds. This is because the more mass, the lower the frequency. Gravity is now pulling with a force of 3.136 newtons rather than a previous force of 2.352 newtons. With the bottle now only 1/3 of the way full, the mass is equal to 160 grams. This has decreased the period to 0.98 seconds. The gravity is equal to 1.568 newtons, pulling the bottle down. I will now demonstrate how the spring constants change the rate at which the rubber band bounces. The first band is 0.737 meters long and has a period of 1.4 seconds. I have removed 2 rubber bands, making the length of the bands equal to 0.559 meters. This has changed the period to 1.18 seconds. This is due to the fact that since the spring constant has now increased, the bottle has less distance to travel in a certain amount of time. I have now removed 2 more rubber bands. making the length equal to 0.432 meters long. This has decreased the period to 1 second. I'll now move on to how different amplitudes do not affect how the mass spring system oscillates. Here I have rubber bands that I have stretched out an additional 0.076 meters. The period will remain 1.18 seconds. I have stretched out the rubber bands an additional 6 inches. The period remains at 1.18 seconds. This is because the more amplitude, the longer the distance, but the distance and speed will cancel each other out, leaving the period to be the same. Finally, I stretch out the bands an additional 10 inches. The period, again, remains at 1.18 seconds.